This presentation is the second half of Module 7 in Chem for Bio at Northern Virginia Community College Annandale campus. And this second half of Module 7 continues with solvents and solutions. But in this module, we discuss solute concentrations, particularly in water-based or aqueous solutions. And then we spend a couple minutes talking about reactions in which water actually takes part instead of just being the solvent. Since biological reactions occur primarily in water, we often need to know not only the identity of the solute, but we need to know its concentration. That's because the concentration of a solute in a solution determines things like the rate of the reaction, the actual amount of product that can be produced, and the rate and type of movement of substances into or out of cells through the semi-permeable membrane. We'll also need to realize that in some cases there are ranges of concentrations where the solute, instead of being beneficial or productive, becomes less than safe or possibly even toxic. So how do you describe a concentration in a solution? It's very simple, it's very general. We need to describe the amount of solute per amount of solution. Now, the definition of amount depends on the application. At the most basic level, we need to be able to describe the number of solute molecules. And for this purpose, we use the definition of a mole. A mole is a counting unit. It's just like a dozen. But whereas a dozen means 12, a mole means 6.022 times 10 to the 23rd. It is a huge number, and it is used almost exclusively to describe molecules or atoms or ions. Because molecules and atoms and ions are so tiny, we need a very large counting unit to describe enough of them to have them have substance, to be visible. So a mole of anything is 6.02 times 10 to the 23rd of that thing. We call it Avogadro's number. How is this definition of a mole used? Well, this will take a couple slides. First things first, you can actually describe the weight or the mass of a molecule simply using the molecular mass. The molecular mass is the sum of all the atomic masses for all the atoms in the molecule. We describe it in terms of Daltons, which we discussed in a previous module. A Dalton and an atomic mass unit are essentially the same thing. So an example is given for you on the slide. The molecular mass, so the mass of one molecule of carbon dioxide, is simply the mass of the one carbon atom, 12.01 Daltons, plus the mass of two oxygen atoms, 16.00 Daltons times 2, to give us a total of 44.01 Daltons as the mass for each carbon dioxide molecule. Well, we haven't related that yet to the concept of the mole, but in the next two slides we will. One other sample calculation for a biological molecule. Let's say we needed to know the mass of one molecule of sucrose, or table sugar. Well, the formula is C12H22O11. So we need to take the mass of 12 carbon atoms, add to it the mass of 22 hydrogen atoms, and add to that the mass of 16 oxygen atoms. You add them up and you get 342.3 Daltons. Realize we're just pulling these atomic masses straight off the periodic table. We covered that in a previous module. So now, let's say you want to weigh out 1 mole of sucrose. How do you convert Daltons to grams? Because of course grams is the most convenient way to weigh out anything. You use a laboratory balance, you record the answer in grams. Well, we have to do some conversions. And the handiest conversion you have as biologists is the fact that 1 gram of anything is equivalent to 6.02 times 10 to the 23rd Daltons. So there's that Avogadro's number again. And it's a very, very handy shortcut. So you can see what you do is you set up this conversion as a series of fractions or ratios. You know that there's 342.3 Daltons per molecule of sucrose. You know that 1 gram of sucrose has a mass of 6.02 times 10 to the 23rd Daltons. And you know that 6.02 times 10 to the 23rd molecules is equivalent to 1 mole. You set up these relationships in fraction form, and you find out that the units you don't want cancel. And in the end, you find out that 1 mole of sucrose has a mass of 342.3 grams, which is very easy to weigh out on a laboratory balance or a laboratory scale. If you are still confused by that series of conversions and how it works, please look at this highlighted, color-coded, step-by-step walkthrough. You need to remember that when doing algebra, conversions of this type, that both the arithmetic values and the units that appear in the numerator or the denominator of these fractions, they can cancel out when multiplied together or divided. So look at what cancels out. You start with 342.3 Daltons per molecule. You use the next ratio or the next fraction, 1 gram per 6.02 times 10 to the 23rd Daltons. Well, the Daltons in the numerator and the denominator and the top and the bottom of the fraction cancel. You continue with the next relationship with the next fraction, 6.02 times 10 to the 23rd molecules per mole. And you find that the value of 6.02 times 10 to the 23rd cancels, and you find out that the unit of molecules cancels. And in the end, you complete the algebra, and you find out that numerically it's 342.3 grams, and that the unit in the denominator is mole of sucrose. So the bottom line is you can calculate the mass of 1 mole of any compound. The mass of 1 mole of any pure substance is equal to its molecular mass in units of grams instead of Daltons. This conversion works every single time. So now how do we describe actual concentrations? One of the most common concentration units is something called molarity. It's abbreviated with a capital italicized M, and it is defined as the moles of solute per liter of solution. Well, in the previous 2 slides, you just figured out how to calculate moles of solute. Now we only need the liters of solution. It's very straightforward. If you have 1 mole of sucrose, which you now know is 342.3 grams of sucrose, you put it in a container, and you add enough water to bring the total volume up to 1 liter. You mix it, and you have a 1 molar solution of sucrose in water, or of aqueous sucrose. Please note that when you physically do this in the lab, you don't add a liter of water. You put the solute in a container, a 1 liter container, and you add enough water to bring the total volume up to 1 liter. That's because the solute actually takes up space. It contributes to that volume, so you usually don't need the full liter of water. You just add enough water to bring it up to a liter. So now, if you wanted a 2 molar solution, 2 moles per liter, you would simply add 2 moles of sucrose, so 2 times 342.3 grams. And again, add enough water to bring it up to a 1 liter total volume. So molarity is straightforward. It's easy to calculate. And molarity works very well with non-electrolytes, with molecules. But we have to have another concentration unit definition, and that is of osmolarity. And we use osmolarity to describe the number of particles, or the moles of particles, per liter of solution. What osmolarity does is it reflects whether the solute, the substance being dissolved, whether it is a non-electrolyte, like sucrose, or whether it's an electrolyte. Remember, in a previous module, we talked about how electrolytes are formed because the compound not only dissolves in water, but it also dissociates into its constituent ions. So realize that if dissociation occurs, the number of particles in solution that can undergo reaction actually increases. Common non-electrolytes are the biomolecules like glucose or sucrose, any of the carbohydrates, amino acids, small protein molecules. The common electrolytes, on the other hand, are the salts. Sodium chloride, which dissociates into 2 ions. Calcium chloride, which dissociates into 3 ions, 1 calcium ion and 2 chloride ions. Any salt you can think of is going to dissociate, and its osmolarity is going to be larger than its molarity. So for example, if you're looking at a non-electrolyte like glucose, 1 molar glucose is also 1 osmolar glucose, because when the glucose dissolves, it just dissolves. We don't make more particles. But on the other hand, 1 molar sodium chloride, well, when the sodium chloride dissolves, it also dissociates and makes 1 molar sodium ion and 1 molar chloride ion, which means its osmolarity is 2. Carrying on in that theme, when we dissolved calcium chloride, since it dissociates into 3 total particles, 1 calcium ion and 2 chlorides, 1 molar calcium chloride actually results in 3 osmolar solution. 3 particles for the price of 1. So that's pretty much it for concentration. Any other concentration units are simply based on the same concept, amount of solute per amount of solution. Sometimes they're described as amount of solute per amount of solvent, but again, it depends on the application. Here's just a couple quick slides about when water doesn't just play the role of the solvent. In most biological systems, in most biological reactions, water does not react. It's just the transportation system. It's just the solvent. But there are occasions when water does react. Sometimes we want it to, sometimes we don't want it to. One classic example from inorganic chemistry is that water reacts, often violently, with the active metals. The active metals are those on the left side of the periodic table: sodium, potassium, rubidium, magnesium, calcium, strontium. When you take a reactive metal and place it in water, it doesn't simply dissolve. It reacts, and the reaction can be violent. The example given here, you take a chunk of solid sodium, you place it in liquid water, it reacts violently. to form a solution of sodium hydroxide, which is a very strong base. We also call it lye. We use it as drain cleaner. And the other product is hydrogen gas. Well, the third product, which is not a compound or an element, is heat energy. And the formation of the heat energy is so severe that it actually ignites the hydrogen gas. And so you see in the photo attached, that is a photo of the reaction of a chunk of sodium metal with water. It ignites the hydrogen gas, generating a huge amount of heat. It's very dangerous, but quite impressive. And this happens with any active metal. So calcium. If you put calcium metal in water, you get a similar reaction, a similar result, which means anytime you're talking about the calcium level in your blood, you are not talking about the concentration of calcium metal. You're talking about the concentration of calcium ion. Whatever you do, don't put calcium metal on your tongue. One other reaction in biological systems that is important and involves water is the hydrolysis reaction. This is a very quick intro to hydrolysis. Depending on your course, you will study it in the classroom, and we will end up reviewing it on future modules. When you have a polymeric or just a larger biomolecule, such as a carbohydrate, the bonds that combine the smaller units together can often be broken by addition of water. The example given here is a disaccharide, so a simple sugar, maltose, can be hydrolyzed by water. So you take the maltose molecule, you want to break the bond between the two rings. You add water in the presence of the appropriate enzyme, such as maltase, and the water molecule breaks the linkage, the glycosidic linkage, between the two monomers that make up the maltose molecule. And what you end up with, upon addition of water, is a formation of two glucose molecules, which are monosaccharides. An analogous reaction happens in peptides and proteins. The peptide bond between two amino acids can also be cleaved or broken by addition of water, by hydrolysis. You add the water in the presence of the appropriate enzyme, and you can get back the individual amino acids.